Hello, welcome to a new lesson. Today we are going to talk about oscillations, and the specific topic is the vibrating string. Um, to explain what this topic is about, we are going to think that we have a string that is fixed on the edges. I mean that, well, this string is going to vibrate, but the external points that are here at the left and the right, well, they are not going to move, right? So the string is going to be oscillating like this, maybe. And what we want to do is to describe the displacement of the string measured from the origin at the level y equals 0, right? So we want to find a differential equation that will allow us to describe the motion in the y-axis of this string, right? So again, this is moving up and down all the time. And the external points are always fixed. Okay, so from that fact, we can say immediately that y evaluated at x equals to 0 and at any time t will be equal to 0, and that y evaluated at x equals to L and the time will be equal to 0, where L is, of course, the length of the string. Notice that, well, we are going to have some strain on the string, right? It will be a force that is applied to every point of the string, and this force will be in the x direction and the y direction. I mean that it will have two components like this. So for example, we can name this strain as tau of x, which is a function of the position, right? So you need to think that if this strain is too strong, well, it will make the oscillations to be too small, right? I mean that this y will be very small if this tau is big. So to study this problem, we are going to assume that this tau is big and the oscillations will be very, very small. Okay, so this will be like maybe the vibration of a guitar string, where the strain of the strings is very big, right? So when you make some force on a guitar string, you see that the oscillations turn to be very, very small, right? So this is the kind of motion that we are going to study in this video. So the string is moving up and down to a limit value of y, which will be named as the letter h, right? Which is the maximum height that the string reaches. Okay, so from here will be minus h. So again, a mathematical way to describe that the oscillations will be small is to compare these oscillations with the total length of the string, which is L. So we are going to assume that h is much smaller than L. Okay, so this will be an important assumption that we need to make to find the differential equation. On the other hand, we just need to say that, well, this string will be a flexible string and elastic. I mean that, well, it is not going to be broken in all the process, right? So in other way, we will not be interested in finding any differential equation. So the string is going to be flexible and elastic. With elastic, I mean that, well, the string returns to its position without losing kinetic energy. Okay, so for example, we can study the case where, well, we have the string like this in the initial position without any force applied, and then we maybe apply a force to the string at the middle of the string, right? Where this distance is L divided by 2, right? Okay, so at this point, we take the string to its maximum capacity, where this is h, and then we drop the string and it starts oscillating, right? But in this manner. Okay, so yeah, just to see how to introduce an example of a kind of motion that this string can make. Okay, so in general, we can say that at any time t, we will have that the string is in this position. Let's say that it's something like this, where this is, of course, x equals to 0, x equals to L, and maybe this is x equals to L divided by 2, right? So this is at the time t. Okay, so we can establish an arbitrary point, let's say maybe this as x. In that case, this point will be y of x comma t, and maybe another point, let's say making a little displacement after this x to be x plus delta x, and then this will be evaluated at y of x plus delta x comma t. I mean that, well, we are taking two different points of the string, but at the same time t, right? That is important. So like I mentioned at the beginning of the video, we are going to have at any point of the string some strain, right? That we will name with the letter tau. And this strain will be dependent on the portion of a string that is beside the point from where we are measuring the strain. I mean that if we look to this point of the string, it will be suffering some kind of strain that will be in this direction from here due to the portion of a string that is right to this element. And then there will be another strain over here, right? From the portion of a string that is left to this piece of a string. So let me make this in another picture. So here we will have the portion of a string that we are interested in that is suffering a right strain and then a left strain, right? That, well, it has an inclination measured with respect to the x-axis. So we can have here an angle theta 1, maybe, and then from here we will have an angle theta 2. So as we can see easily, there will be two components of the strain that is applied to this portion of a string, and also here we will have two components of a strain. Okay, so it is easy to see that, well, the x components of the strain, well, they are not going to move the string. I mean that they do not perform any work in an idealized way. Actually, in real strings, there is actually a little motion in the x direction, but we are going to consider that that motion is not big enough to be considered, okay? So we are only going to consider the components in the y direction. I mean, this one and this one. Okay, perfect. Other thing that we are assuming here is that, well, we have this strain, right? But any point of this string, well, it has some value of tension. So the tension is going to be a function of the position, right? So what we are doing here is like considering this portion of a string as that point x. Later on, we are going to take the distance x to be approaching 0, right? To consider this as just a point of the string. Okay, so we can decompose these two forces, but let me write the reference system over here where this is x and this is x plus delta x, right? So this means that the tension that we are evaluating here will be the tau of x plus delta x, and then from here we will have tau of x. Perfect. So the y components of these two strains will be This one over here is tau of x sine of theta 1. And then from here, we will have that this is equal to tau of x plus delta x times sine of theta 2, right? As is easy to notice. Okay, perfect. Again, notice that what we are measuring with these angles, theta 1 and theta 2, is the inclination of the tangent to the string, right? I mean that if we have this string, we have a tangent line over here, and what we are doing is to measuring the angle of inclination of this tangent. So this means that, for example, if we go to another portion of a string and draw a tangent line, again, we are going to be measuring the angle with respect to the x-axis. So what I want to what I want you to see here is that theta is actually, well, theta 1 and theta 2 are functions of x, of the position, right? Because we can see from these two examples that depending on the position of the string we are, well, theta will be will take some value or another one, right? Okay, perfect. So another thing that we need to say is that, well, you know that in the Newton's second law, we need to introduce the mass of the object. But in this case, looking that we're talking about a string, we are going to talk about the linear density of the string, right? So the mass is going to be some linear density times some kind of length, right? But if we are looking to a piece of a string, that we can say that it will be some delta S, well, this mass is going to be equal to the density times delta S. Okay, perfect. So remember that we mentioned that we were only going to study the motion in the x direction, so we are interested in the acceleration in the y direction. Okay, so if we consider Newton's second law, we will have that the mass, which is rho delta s, times the acceleration, which is, well, it will be the second derivative of y with respect to time, of course. Well, it will be equal to the sum of the forces in the y direction. So again, we are going to consider that, well, the force of gravity is of no consideration because it is very small compared with the force, well, the tensions tau. Okay, so it can be maybe look that we are making a lot of approximations, but even though we are making a lot of approximations, well, the differential equation that we are going to find actually describes the motion of strings like guitar strings or violin strings. So it works. I mean, yeah, there are a lot of assumptions, but it still works out. Okay, so in this step, we need to write the elements of the forces in the y direction that are, in this case, minus tau of x sine of theta 1, and then plus tau of x plus delta x sine of theta 2. And looking that we mentioned that theta 1 and theta 2 are functions of the position, well, it's easy to see that theta 1 is equal to actually theta of x, and theta 2 is equal to theta of x plus delta x, right? Because theta 2 is at the point x plus delta x, right? And then theta 1 is at the position of x. Okay, perfect. So we are going to rewrite this equation in the next way. We are going to say that rho delta s divided by delta x times the second derivative of y with respect to time is equal to tau of x plus delta x sine of theta of x plus delta x, and then minus tau of x sine of theta of x, like this. And yeah, we're going to divide by delta x. Notice that this structure that we have here already has the form, or almost has the form of a derivative, right? By using the definition of the derivative, we see that this thing is almost the derivative of a function. We just need to take the limit as delta x goes to 0. And like I mentioned before, that is the property that will allow us to consider that this portion of a string is actually just a single point of the string, because as delta x goes to 0, this point approaches x, and then this portion of a string becomes just a singular point. Okay, so what we are going to do now is to take the limit as delta x goes to 0, right? So notice that if we do that, this element x is going to be approximately equal to delta s, right? So we will have that delta x is approximately delta s. Okay, so this thing over here is going to be equal to 1. It is like doing this element and then smaller and smaller. So if we do that, we see that delta s approaches delta x, right? It's like making the displacement of the string as small as possible. So that means that this element is going to be equal to 1. Okay, so if we do that, here we are going to have the limit as delta x goes to 0. And then here we will have the limit as delta x goes to 0. So from this left-hand side of the equation, we will have rho, the second derivative of y with respect to time, equals 2. And here on the right-hand side of the equation, we have exactly the definition of the derivative with respect to x of the next function. It will be tau of x that multiplies sine of theta of x. Okay, so we are almost there. We just need to establish some other thing. We know that the slope of a tangent line is equal to the tangent of the angle of inclination, right? What I mean is that we know that tangent of theta is equal to the derivative of y with respect to x, right? If we have a curve, we know that, well, the derivative, which is equal to the slope of this tangent line, m, well, is equal to the derivative, but it's also equal to the tangent of theta, right? So with that, we can establish this relation over here. But from this relation, we can establish that sine of theta divided by cosine of theta is equal to the derivative of y with respect to x. And then that sine theta secant theta is equal to the derivative of y with respect to x. But from here, we can say that tangent squared theta is equal to the derivative of y with respect to x squared, which is equal to 1 minus secant squared theta. So from here, we can say that secant of theta is equal to 1 minus the derivative of y with respect to x squared, all this under a square root, like this. And then we are going to take this element to this equation that we found to get that sine theta is equal to the derivative of y with respect to x, that is divided by secant of theta, but that is the square root of 1 minus the derivative of y with respect to x squared. So remember that we are considering small oscillations. So if oscillations are small, we can say that the inclination of the tangent line, which is the derivative, well, is small, right? This inclination is small. So that inclination is represented by the derivative of y with respect to x. I mean that, for example, if we have a smaller oscillation, we see that, well, the inclination is practically 0. So if we raise that inclination squared, well, that is also going to be close to zero, right? Actually, it's going to be much smaller than just taking the derivative of y with respect to x. Okay, so what I mean is that this element is almost zero. So we are going to consider that, well, it doesn't contribute too much. So with that, we can conclude that sine theta is approximately the derivative of y with respect to x, but we said that tangent of theta is equal to the derivative of y with respect to x. So that means that in small oscillations only, well, sine theta is approximately tangent theta. Okay, perfect. So with that, we can go back to the differential equation that we constructed to take this sine to be equal to, well, tangent theta, which is equal to the derivative of y with respect to x. So we can conclude that rho, the second derivative of y with respect to time, is equal to the derivative with respect to x of tau of x times the derivative of y with respect to x. Okay, so this result is known as the equation of vibrating string. Okay, so this was like the main goal of the lesson. Perfect. So it is the differential equation that describes actually the motion of a guitar string, maybe. So it is very, very, very important. Now, a very important case is where the tension is a constant. What happens in that case? Well, we are going to have that rho, the second derivative of y with respect to time, is equal to the derivative. Let me take that tau out, the derivative with respect to x of the derivative of y with respect to x, which is equal to tau, the second derivative of y with respect to x. So we see that, well, we have the structure of a wave equation, which is not very surprising because we know that a string of a guitar maybe moves like a wave, or it can be represented with the wave equation, right? So we can say the next. The second derivative of y with respect to time is equal to, it will be tau divided by rho, the second derivative of y with respect to x squared. And this is very, very interesting because we know that the element that is the coefficient of the second derivative of y in this case with respect to the space coordinate. We know that this coefficient represents the velocity of the wave, right? So we can say that if you already know the structure of the wave equation, you can identify easily that the velocity is equal to the square root of tau divided by rho. Okay, and this is very, very interesting because this is telling us that the wave associated to the oscillation of the string, well, it has some speed that depends on the tension that is applied to the string and divided by the linear density of the string, right? Perfect. So that is very, very interesting. Okay, perfect. So just to finish this lesson, we are going to establish what are the initial conditions of the example that we mentioned at the beginning of the lesson. Remember that we said that we have the string that is fixed to the external points, x equals 0, x equals L, and we applied a force to rise up this string up to a height h, and that makes the string to take this triangular form. So this is h, and this is at the middle point, x equals L divided by 2. Okay, so what we want to do is to establish some equation of x that will tell us the displacement of the string at the time t equals 0, right? So this is at t equals 0. Okay, so as you can see easily, well, this is just a straight line. So we are going to use the very famous equation to describe straight lines. We know that, for example, this point has the coordinates h, comma, L divided by 2. This is the point 0, 0, and this is the point L comma 0, right? So we will have that y of x evaluated at t equals 0 is equal to, and we will have two pieces of information, right? So to find the first equation, we are going to consider this point, and we are going to have that y minus 0 is equal to the slope m times x minus 0. But that slope can be easily calculated as h divided by L divided by 2, right? And this is equal to 2h divided by L. So y is equal to 2h divided by L times x. Okay, perfect. So this is the first part of the function y of x at t equals 0. So it is 2hx divided by L if x is on the interval 0, L divided by 2. Okay, perfect. And then how are we going to find the other equations? So we will have that y minus 0 is equal to the slope of this line times x minus L, right? Minus L. So from here we will have that m is equal to h minus 0, right? And then L divided by 2 minus L. So we have h divided by minus L divided by 2, and this is equal to 2h negative divided by L. Perfect. So we will have that y is equal to minus 2h divided by L times x minus L. So this can be seen as 2h divided by L, L minus x. Perfect. So we write that here. We have 2h divided by L times L minus x. If x belongs to L divided by 2L. Recall that these two functions need to match at the point x equals to L divided by 2. So that's why I used closed interval or the brackets here at the point L divided by 2, right? Because, well, it is a continuous function at that point, so it doesn't matter. Perfect. So with this, we can establish the initial conditions of the string, or the initial positions of the string before the motion begins. Okay, perfect. So I think that with this is enough to introduce the concept of vibrating string. We have found the important equation that describes the motion. And just a quick example to see what are the initial conditions of the vibrating string. You know that this can represent maybe the motion of a guitar string, or a violin string. So yeah, it is a very famous equation, actually. Perfect. So with this, I think I'm going to finish the lesson. And thank you so much for watching.